Hey guys, we're back and we are starting section 2.9 with using logarithmic expressions. You might have learned this before, but we're going to go back to it because we don't use logs a lot. This is the big idea. And the idea is that a logarithm of a specific base of a value equals a, if and only if the exponential expression b to the a power equals that value of c. So this is an exponential and this is in logarithmic form, okay? So for example, if you had log base 4 of 16 that equals 2, and this is true because 4 to the 2 equals 16. Okay, and we know that's true. 4 squared is 4 times 4, which is 16. Keep in mind, this only works if the base of the log is greater than 0, but it also cannot be 1. Okay, so those are your constraints. Okay, that the base value that we're using cannot be negative. It's got to be greater than 0, but it also cannot be 1. Okay, so let's try a few of these. Let's do an example. Let's write the following as an exponent. So remember to go from logarithmic to exponential form, I like to say we go left, right, middle. So in base form, we go the left value, which is the base, to the rightmost value, which is the value, equals the middle value. So we say 3 to the 4 equals 81. And if you want to check this in your calculator, 3 times 3 times 3 times 3 is in fact 81. So for example, example 2. So again, logarithmic to exponential, we're going to take 16 left to the right is the power equals the middle. So 16 to the 1/2 equals 4. Remember, this is correct because if we remember, anything that's a fractional exponent becomes a radical where your denominator is your index and your numerator is the power on everything. So this also becomes the square root of 16 to the 1, which is 4. All right, let's look at this next one. It says, let's rewrite the following exponents as logarithms. So again, we're still going to use left, right, middle to go from exponent to logarithmic form. So we're going to write, to go to logarithmic form, we're going to start with the log of the base. So instead of the base of the log, the base number becomes the base left of the right. So this becomes the middle value equals 1/3. So this means that we need 5 of log base 125s to equal 1/3. For this next one, again, to go from exponential to log form, we're going to write log. The base number becomes the base of the log. So we go left, right, middle equals 3. And that's because we need 1,000 log 10s to equal 3. Keep in mind, this shows you something really important. Whenever we have a log with a base 10, we call this the common log, which is a base 10. So when you just see log 1,000, just know that there's an invisible 10. We don't put log base 10 because that's just implied that it is base 10. So when we say log base 10 of something, we just use log. In your calculator, the log key is also going to be implied that it's a log base 10. Okay, so let's start using these ideas to find the values here. So if they're saying, all right, let's move on. Find the value of each log. So to find the value of each log, we know it has to equal something. So we know log with no base is log base 10. So if I rewrite it like this, I can say 10 to the exponent equals 100. Left, right, middle. Well, now my goal, once I've got it written like this, is you're going to get the base to the same, or the bases to the same number. So how can I make it so that the base 10 and the 100 have the same base? Well, I can rewrite 100 as 10 squared. So 10 to the x equals 10 squared. Once I have those same bases, I know that x has to be equal to 2 in order for this to be true. Let's look at number 6. It says log base 2 equals 1 over 32. So again, we're going to set this equal to some unknown value, and we're going to write this in exponential form. So base of 2 to the y exponent equals 1 over 32. So again, we want to get the bases the same. So how do I get 2 and 1 over 30? So first of all, I know 1 over 32 is the same as 32 to the negative 1. So anytime we see a fraction, we want to turn that into a negative exponent. Once I have that, I know 32 can be related to 2 as 2 times 2 times 2, which is 8, times 2 again is 16, times 2 is 32. So I know 2 to the 5th equals 32. So I can say 32 is actually 2 to the 5th, to that negative 1 power. Well, I know 2 to the 5th to the negative 1 is really just 2 to the negative 5. So now I officially have that same base, and I can say that y equals negative 5. And you can also verify this in your calculator. Let's look at this one. So we're going to set this equal to, let's call it z. So we're going to say 4 to the z equals 25. So there's no way to get a 4 and a 25 to have the same base. So we can't do this by hand. We have to use a calculator. So in order to use a calculator for this, I'm going to give you something called the change of base formula. And that's because your calculator can quickly and easily only do a base of 10. So that log button in your calculator is only a base 10. Here we have a base of 4. So we need to get this into a log base 10 somehow. So the change of base formula says this, that if you've got the log of some base and some number, you can change them both to a base, any other base, specifically log base 10, if you do log 10 of the big number c all over log base 10 of the little base number b. So in your calculator, this would look like log base c in parentheses divided by log base b in its own parentheses. So let's try that here. So in order to do log base 4 of 25, I'm going to change this using the change of base formula to log base 10, or common log, of 25, all divided by log of 4. And we're going to put them in their parentheses, put this in your calculator, round it to the nearest 3 decimal places, and we're going to get approximately 2.322. All right, other example, log 39, remember, there's no showing base, we've got an implied base of 10. So we're going to set this equal to some unknown number. We'll call that g. Here's the thing, I can't make 10 and some unknown number g the same base. So we're just going to evaluate this in your calculator. So in order to evaluate this in the calculator, it already is a common log. So we're just going to take log of 39, hit equals, and we get approximately 1.591 to the 3rd decimal place. Okay, turn the page. So you might be asking, okay, we learned all about all this stuff, but why do we use log? So let me just illustrate for you some of the reasons why we might choose to use log versus our traditional linear scale of stuff. So we have this data that we have these 3 content creators who create videos, and this is their average length of their videos in seconds. So if I use a linear scale, so my first scale that I'm going to write on the first one is going to be a linear scale. Remember, linear scales means that like every scale unit equals the same amount in value. So I can see here that the content creator Kelly gets 10,000 approximate seconds for his average video. So if I was going to represent this on the scale, I can see that there's, if I say this is 0, that there's 1, 2, 3, 4, 5 pieces to this scale. So I want to figure out a number that will help me split up about 10,000 seconds evenly. I know if I take 10,000 divided by 5, that would give me about 2,000 each. So on my linear scale, I'm going to let each of these represent 2,000 seconds. So here's 4,000 seconds, 6,000 seconds, 8,000 seconds, 10,000 seconds. So this is our typical linear scale. So if I wanted to demonstrate what this looks like, so Sully makes 505. So if this is about 1,000, here's Sully at about 500. So here's where he's at. Breast is 830, which is a little bit to the right of that breast. Bean is 1,400, so it's about halfway here. And then lastly, we have Kelly that creates about 10,000 and a little bit more seconds of content. So if we look at this scale, the first 3 content creators are really, really close, and then Kelly is way, 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 way longer out of that. So I wonder if there's a better way for us to show what's going on here. Instead of using a linear scale, let's use a logarithmic scale with a base 10, okay? That means this. So instead of going from 0, let's use a log base 10 where it's more exponential. So this could be 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, and 10 to the 5. So even though these are vastly different values, we're increasing by a multiplicity scale of 10 for each of these values. So let's look at to see what we have here. So if I convert these values, let's say, into a log base 10 of 505, if I went ahead and did that in my calculator, so if I go log 10 of 505, we'd get approximately 2.7. Log of 830 is approximately 2.9. Log of 1440 would be approximately 3.2. And log of 10,160 is approximately 4.0. So if I were to put that on my log base 10 scale, it would look something like this. So if we were to graph this on our logarithmic scale, I know 10 to the 2.7 is approximately 505. So I'm going to put this on 10 to the 2.7. So if this is 10 to the 2, which let me show you where that is real quick. If this is 10 to the 2 and this is 10 to the 3, 2.7, if this would be like 10 to the 2.5, here would be 10 to the 2.7. So we're going to put that right here. This is approximately 10 to the 2.7. So we're going to put that here for Sully. For breast is going to be 10 to the 2.9. So that would be about right here. For bean, that would be 10 to the 3.2. So it's going to be over the 3, about right here. And then Kelly would be 10 to the 4.0, so it's about right here. So if we look here, in comparison, this is a little better than the linear scale because the first 3 were so close together and Kelly was so far away. They're a little bit closer now, but what if we used a different linear or logarithmic scale? What if we used a log scale of 5? Okay, so for this one, if I use log base 5, I can turn all of these values and compute them into a log base 5. So for example, if I put it into my calculator, log of 505 over log 5, to put it in base 5, we get 3.9. Go ahead and do that, push pause, and complete the chart for your log base 5. So if you did your log base 5, you should have gotten 4.2, 4.5, and 5.7. So if I were to put that on my log base 5 over here, this would be 5 to the 0, 5 to the 1, 5 to the 2, 5 to the 3, 5 to the 4, and 5 to the 5. So log base 5 of 3.9 is the first value of 505 seconds. So that would be about right here. So that's going to be Sully. And then we've got breast, which is log base 5 of 4.2. And then we have bean, which is log base 5 of 4.5. And we have log base 5 of 5.7. Right here. So that's a little bit closer together. That's an okay expression as well. We can see here, though, that both of the logarithmic expressions showcase the values a little bit better than just a simple linear expression. Okay, so right now I want you to push pause on the video, and I want you to try these 4 problems and see if you get them right. So, and then we'll go over them in class, but I want you to try them now. Go ahead and push pause. Okay, so once you've tried these, let's check to see that you got them right. So if we're going to write this as a logarithm, we're going to say log of base 16 of 8 equals 3/4. To write this as an exponent, we're going to take off the log and take 32 to the 2/5 equals 4. To write this as or to find this value, we're going to replace 5 with x. So we say log base 25 of 5. To find this and evaluate it, we're going to set this equal to some unknown value. And we're going to take left to the right equals the middle. So 25 to the y equals 5. How do I get this to the same base? So I know 25 can be written as 5 squared. So when I see this, remember that this is really to the 1 exponent. I know 2 times y equals 1. So if 2 times y equals 1, we can divide both sides by 2, and we get y equals 0.5. And then lastly, to evaluate log base 6 when x is 12, in order to do this, we're going to have to use the calculator. So we're going to go use your change of base. So you're going to go common log of 12 divided by the common log of 6. Remember, these will go in their own parentheses. And we get approximately, rounded to the nearest 3 decimal points, 1.387. I hope you got 4 out of 4 on that one, and we'll go over it in class. Thanks.